So today, we're going to be looking at position versus time graphs probably all day, okay? We might get to velocity versus time graphs. It kind of depends how things go, all right? So what we need to look at today is what kind of information we can get from those two kinematics graphs, okay, from position versus time and velocity versus time graphs. Okay, understand how graphs and equations show the same information in different ways. Okay, yesterday when we were looking at that graph of position versus time, I showed you how v equals d over t is actually equal to the calculation of slope on a position versus time graph, and that's something we'll go over a few more times today. Okay, and so that is that kinematics equations are derived from graphing. So almost all of the equations that we use are derived from a graph in some way. So one of the things you're going to be required to do with graphs is interpret. And that doesn't require you to do any calculating. It means I can look at a graph and tell what's going on in that graph. All right, so as an example, this is a graph of position versus time here on the left. Okay? So it shows where an object is at various points in time. So what is the object doing between 0 and 1 second? Nothing. Exactly. Okay? Its position is not changing between time 0 and time 1 second. It stays at a position of 20 meters. Okay? In other words, it's stopped. Okay? Or it is not moving, or nothing is happening. I would accept any of those as an answer on the test. Okay? And I very often put a graph like this on there and say, tell me what's going on in each section of the graph. Or tell me what's going on between 2 seconds and 5 seconds, or whatever. Okay? All right, what's going on in this graph between 1 second and 3 seconds? Okay, rising, moving. I'm looking for even more specific. Those are all right, but I'm looking just for even a little bit more specific. It is moving.
It's increasing.
Okay, its position is increasing.
It's moving away from the beginning position.
Moving away from the beginning position. Is it doing that at a constant rate? Yes. Okay. Now, if something's position is changing at a constant rate, okay, so really what's happening here is in the first second, okay, between 1 and 2 seconds here, it went from 20 to 40 meters. And in the next second, it went from 40 to 60 meters. Okay? So its position is increasing at a rate of 20 meters per second. What are the units? What are meters per second? What is that the units for? Meters per second are the units for speed or velocity. So what I'd be looking for as an answer to a question like this would be the object is moving forwards at a constant velocity. I wouldn't even require that you tell me it's 20 meters per second. Okay, although that's not terribly difficult to calculate or even notice from the graph, but I would be looking for moving forwards at a constant velocity for full marks. Okay, if you said moving, that'd be like 1. Okay, moving forward, 2. Okay, moving forwards at a constant velocity, 3. Okay, does everyone kind of follow the difference? Different levels of detail there, right? Okay, what's going on between 3 and 4.5 seconds?
It's moving backwards at a constant rate.
Between 3 and 4.5? 3 and 4.5 is here to here.
It's doing nothing.
Doing nothing, yeah. Position is not changing. It's stopped at a position of 60 meters. Any one of those would be an acceptable answer, okay, in that situation. All right. Now, Evan, the part you were thinking I meant is the last part. Okay, from 4.5 to 6 seconds, the object is moving
Towards the original point at a constant rate.
right, moving towards the original point at a constant rate, okay, or moving backwards at a constant velocity. Okay, and that velocity could be calculated, but it's not necessary if I'm just asking you what's happening. If I ask you to calculate the velocity, then I'd be looking for a number. okay? So we've got to be able to look at a graph and say, here's what's going on in this graph, right? And that involves us being able to look at the graph and go, okay, this is showing where the object is, position, as a function of time. Okay. In which part of the graph, let's say A or B, is the object moving faster? B. How do you know?
Because the length it goes from increasing and stopping is longer on the A.
Yeah, it takes, like, from 1 to 3 seconds, it changes its position by 40 meters, but that takes 2 seconds. Okay, here, it changes its position again by 40 meters, but it only takes 1.5 seconds. Okay, now, probably a lot of you were looking at that and saying the same thing in your head, B is faster, but maybe didn't understand why you thought B was faster. Okay, let me put this idea in your head. It was because the line was steeper. Right? We would naturally look at a steeper line, and our instinct says faster than a less steep line or a shallower line. Okay? Now, the reason we might think that is because on this graph, if you recall yesterday, we said slope equals y minus b over x, which on this graph is final position minus initial position, because position's on the y, divided by time, because time is on the x-axis. That calculates velocity. Okay, so our instinct of looking at a line and seeing that the slope of it is greater, or that it is a steeper line, okay, that means faster, is absolutely right. Okay, in this case, it's actually faster, okay, but on any kind of graph, a steeper line means the change is greater, or the rate of change is greater, okay, in that particular section of the graph. Okay, what's going on this graph? It's still a position versus time graph, but the lines aren't like straight, it's a curve. What is that object doing?
It's moving. It's moving away from its original position at an increasing rate.
Yes. It's accelerating. Okay? It's moving away from its original position, but it's doing so faster and faster. Okay? How can we tell that? Well, remember, on the y-axis is how far the object's going to go. Okay? So in the first second, the object only went that far. Okay? But in the next second, it went further. And the second after that, even further. And so on and so on. Okay? Same time interval, but each successive time interval, the object travels further than it did the interval before. The only way for it to go further in the same amount of time is for it to be going faster. Okay? So this isn't something we want you to memorize, okay? Because there's a real tendency for people to look at graphs and go, oh, I don't like graphs. Graphs are hard. I'm just going to memorize it. Which, for Science 10, okay, you got 2 graphs. So you could probably memorize enough stuff to get by on 2 graphs, although I still see people frequently try to memorize and screw it up. Okay? But when you get to Physics 20, we go over a dozen different graphs. When you get to Physics 30, probably 4 dozen graphs. Okay? It's going to become more and more difficult to memorize what every little bit of every type of graph you might encounter would mean. Okay? It's better to be able to look at a graph and interpret it like we just did. Okay? I looked at this graph and went, okay, this line or this axis tells me how far it's going, and each of these is an equal time interval, and each time interval, it went further than the interval before. If something goes further, it must be going faster. That means it's speeding up. Okay? I don't have to memorize that. I can analyze that and come up with that idea myself. Okay? All right. Now, slope calculations. Okay, we looked at that yesterday. Okay, slope calculations are important. Okay, this is your rise over run calculation here for this particular graph, okay, for a position versus time graph. But as I said, we don't use rise over run in science. Right? In science, we use y equals m times x plus b. Okay, for a linear graph, that's going to help us to get our slope, as long as we solve for what? Which part of this equation is slope? M. Okay, so y value of a point, x value of a point, y-intercept, slope. So if I'm calculating slope, m will be y minus b, or the change in position, divided by the change in time, x. So on this graph, and we just went over this a minute ago, on this particular graph, that means I'm going to be taking my final position, subtracting my initial position, and dividing it by time, which will calculate velocity. Okay? Slope is not velocity on every graph. On the next graph we go over, it'll be acceleration. Okay? The slope of a line on any graph can mean something different. It all depends on what's on the graph. Okay? We always calculate the slope this way. Okay? But what we're subtracting and what we're dividing is different on every graph. Everyone okay with that idea? Alright, and we did a whole bunch of calculations yesterday with y equals mx plus b, so I'm not going to spend a whole bunch more time on that today. So we have a position versus time graph here. Here's some things I might ask you to do on an exam or on a quiz. Okay? So knowing the following things, knowing that displacement is final position minus initial position, okay? Knowing that distance is how far, okay? So the total distance traveled, okay? Knowing that speed is distance over time, and that velocity is displacement over time. I want you guys to calculate for me the total displacement of this object over the entire trip. Okay, I want you to find the total displacement of the object over the whole trip. You should all be done. It's 0. Okay, now probably a bunch of you are going, huh? Okay. Why? Why is it 0? Okay. Displacement is your final position minus your initial position. What's my final position? 0. What was my initial position? 0. What's my total displacement? 0. Okay. Here's the next thing I'm going to ask you to calculate. What's the average velocity over the whole trip? You should all be done. Velocity is displacement divided by time. What did you just tell me the displacement was? Right, so what's the velocity? Right, okay, they went someplace and then came right back to where they started. That means you have no overall velocity. Okay. I want you guys to calculate for me the total distance traveled. That's going to take a little bit longer. Okay? Total distance traveled. How far does this object go over the whole trip? And remember that direction is not important here. Okay? You've got your positions on the y-axis. You don't need time for what we're doing. Okay. What's going on in this graph? And for now, ignore the little dotted triangles. I've got a curve, and then a different curve, and then a different curve. What's going on here? It's like the power band of a car after it blows its engine at B. what do you suppose this might be a graph of? I would never ask you that on a test, but it's not really fair. That's a graph of what I was just doing. Throwing an object up into the air and then letting it come back to me. Okay? So this first part here, part A, until we get to about here, is me pushing the marker. I'm accelerating the marker, making it go faster and faster and faster. Okay? Right here is where it leaves my hand. And as soon as it leaves my hand, what's happening to it? Well, yeah, I mean, it's moving upwards, but is it going faster or slower? Right, gravity has grabbed it, right? Gravity is now slowing it down, slowing it down, slowing it down until it's stopped, okay? And then it falls back down to my hand. That's why the two halves here look exactly the same. They're a mirror image of each other because they're both acceleration due to gravity. Okay? The last part is me catching the marker and bringing it to a stop. How do I know it comes to a stop? What does the line look like right here? It's flat. Okay? So I slow it down, and it stops. Okay? Not moving anymore, so the line gets flat. All right, so here's what's going on in this particular graph. Acceleration. Several different ones, in fact. Anytime we have a curved line on any graph, it means that something is changing, but it's not changing at a constant rate anymore. Okay? Changing at a constant rate would mean I get a line like this. Okay? That would show something, the position of the object changing at a constant rate. Okay? Because it goes up by the same amount every single time. Right? That's not what's going on here. Okay? Here we have something's position is increasing, but it's increasing at an exponential rate. Okay? Every second it goes further than it went the second before. Okay? Up to this point here, at least for part A. Everyone all right with that idea? Okay, and then once we get to here, we see that that line is no longer going up. Okay, it's no longer like getting steeper. It's actually getting flatter. Okay, so if I'm like drawing a tangent, you guys heard of that term before? Okay, a tangent is a line that touches a curve but doesn't cross it. Okay, and that means that wherever it touches the curve, it's got the same slope as the curve does at that point. Okay? So if I use this line to be a tangent, okay, and I put it against the curve, okay, right here where it intersects at that x, okay, its slope, the slope of this line is the same as the slope of the curve. Right? If I do that further on, then the slope will be greater. Okay, so here it's touching right there, and I can see this, it got more inclined. Okay? So remember, slope of a line tells us how fast an object is going. If you've got a curve that's getting steeper and steeper and steeper, it means the object's going faster and faster and faster because the slope is getting greater and greater. Okay, so what I'm going to explain to you is the only thing that I understood in university calculus. Okay? I took one university calculus course. I never took any other math course after that. Okay? I realized my limitations. So, to a mathematician, a curve is an infinitely large number of infinitely small straight lines. Kind of like if you're watching a low resolution video on YouTube, or if you've got bad connection and your data rate's really slow. What can you see? If it's low resolution, you can see the pixels. Because a computer is a mathematician. It makes curves with little tiny squares. If you're watching something in, ultra high definition, like 4K, the pixels are so small that we can't even see them. So images look really, really sharp. If you're watching something in like, was it 1.2K or something like it's terrible, whatever. It's awful resolution, then you see all these squares everywhere. Okay? Well, if I looked at this curve like a mathematician looks at it, I would see every little piece of straight line. Okay? Because that's what they see when they look at a curve. Everyone follow me so far? Okay? So when I do this thing with the tangent line, okay, I'm recognizing that when I put this tangent line against the curve, I'm parallel to the little tiny straight line that exists at that point. Okay? So we're saying it gets steeper and steeper and steeper. Once we get past this point right here, I told you that it's starting to slow down. Okay? And it's starting to slow down because the line's getting shallower and shallower until it's flat. Okay? I mean, if I draw a tangent line that just touches that curve right at the top of it, it's horizontal. Okay? Because when you throw something up in the air, okay, at the very top of its flight, that's where it stops for just an instant before it turns around and falls back down. Right? As soon as it leaves my hand, slowing down, slowing down, slowing down, stops, speeds up, speeds up, speeds up, and comes back to my hand. Okay? It's that whole what goes up must come down thing. Okay? In fact, if I throw this and it leaves my hand at 2 meters per second, when it comes back to my hand, how fast will it be going? 2 meters per second. Okay? Because everything about that movement is identical, except direction. Okay? The acceleration is the same, the distance is the same, okay? So the initial speed and final speed also have to be the same. Okay, and then the same thing is true down here. I said where I'm stopping it. Okay? If I draw a line that is tangent to the curve there at the very end, it's also flat. Okay? You're not going to have to do any calculating in Science 10 with a curved graph, but you do have to understand what it means. Okay? Curved graph, regardless of whether it's position time, velocity time, growth versus steroid use, whatever, if it's curved, okay, it means that the rate of change is changing. Okay, it's not constant. It's getting bigger or it's getting smaller. Okay, on a position versus time graph, it means the rate of change of position, velocity, is getting bigger or smaller. Okay, I want to have you guys do a couple of things here with position versus time graphs. Why are these all velocity? There we go. Okay, so with this position versus time graph, I want you to calculate those things. I want total displacement, total distance, average velocity, and average speed. Okay, the answers are there in bold, so you can see if you did it right. Right? I'll give you a few minutes to do those calculations. All right, so first thing we want to find is the total displacement. Okay, and we know that total displacement is final position minus initial position. The final position of this object is 0.5 meters. The initial position of this object is 0.2 meters. Okay, that's going to mean positive 0.3 meters. Is the positive important? Is displacement a vector quantity? Then the positive is important. Okay, that's the only vector we're given in the question. Okay, we're not told north, south, left, right. We have to go with positive and negative. All right, we want to find the total distance traveled. Now direction doesn't matter, but we got to do it piece by piece on the graph. How far does it go here? 0. Okay, then it goes from 0.2 to 1.0. So that's 0.8 meters. How far does it go here? 0. Okay, then it goes from 1 down to 0.5. Okay, 0.8 plus 0.5 is 1.3 meters. Okay, total distance traveled. Okay, and then to get your average speed and average velocity, we just plug into the formulas. Average velocity is total displacement, which I already calculated, divided by total time, which I can read off of the graph. So, 0.3 meters, positive 0.3 meters, divided by 7 seconds, should give me my 0.04, positive 0.04 meters per second. Okay. And then, for speed, speed is total distance divided by total time, 1.3 meters divided by 7 seconds, and that comes out to 1.19 meters per second. Okay, no direction needed on the speed because speed is scalar. Okay. That is very much like what I would ask you to do. Give you a graph like that on a quiz or a test and make you do exactly those same calculations. Right? Are they any different than what we were doing before? Okay. The only difference here, guys, is I was giving you questions that were a paragraph. It was read this story and get the numbers from it. This is the, here's, you don't have to read the story. Just get the numbers from the graph. Graphs are faster. All right, I want you guys to try that one. Same idea, slightly different graph. Okay, give it a try. Okay, so for this one here, okay, we want to first off calculate the distance traveled between 0 and 90 seconds. So that means we're going to this point right here. Okay, because that's where 90 seconds is. Sorry, that's 80 seconds. This point right here would be 90 seconds. All right. So the total distance traveled. So we go from 0 to 400. So that's 400 meters right there. How far do we go here? 0. Okay, and then we go from 400 back down to 200. So that's another 200 meters. So we're looking at 600 meters. Okay, and then we're looking for the displacement from 20 seconds to 80 seconds. So from this point to this point right here. And displacement is final position minus initial position. So we're going to have 300 minus 200 equals positive 100 meters. Okay, everybody all right with that? And then the speed over the whole trip. Okay, well, it goes 400 up and 400 back, so the total distance traveled is 800 meters. Everybody okay with that? Right? And that takes 100 seconds, so 8 meters per second would be our average speed over the whole trip. And our average velocity over the whole trip is 0, because our final position is, and our initial position is, right. Okay. We're getting the hang of how to read these graphs. Try this one. It's a little bit different because it goes into the negatives. So let's have a look at this one. So the first thing they want to know is the total, or the displacement from 0 to 4 seconds. So here's our initial position, here's our final position. -4 minus 0 is -4 meters. So our displacement to 4 seconds is -4 meters. Okay. Total distance traveled. Okay. Well, 4 meters, 0 meters, and 10 meters. So 14 meters would be our total distance traveled. And then average velocity, average speed over the whole trip. Well, we just figured out the hard part, so it's 14 divided by 6, which will give us 2.3 meters per second. And if we want to get our average velocity, we take our total displacement, which we haven't calculated yet. So my final position is here at 6 meters. Initial position was 0, so displacement is +6. Total time, 6 seconds, +1 meter per second. All right, so same kind of thing. For irregular graphs, that's the kind of question you're going to get. For linear graphs, you're going to get questions like we worked on yesterday, where you got y equals mx plus b, and I'm asking to calculate something that's either on the graph and not where a point is, or off the graph, okay, or something like that, and you have to manipulate y equals mx plus b and solve. So those are the two ways you're gonna get graphing questions, right? So we've gone over position versus time today. We're gonna go over velocity versus time graphs tomorrow. And then on Monday, we're gonna do a lab with position versus time graphs. So we're gonna run these little motorized carts down the atrium, okay, and we're gonna record their positions as a function of time and get data that we can use for graphing and then doing some analysis with that, with those graphs. So, you guys don't have anything coming due yet, but obviously that lab report for that lab will probably be due either late that next week or early the week after, okay? So that stuff is all coming up for you, okay? Make sure you're reviewing regularly so you don't get behind, you don't have as much to do when exam time comes later. Okay, we'll call it a day there, guys.